These are the notes for AP Calculus on the topic of common Maclaurin series with derivatives. So on this one, we're given that the function g has derivatives of all orders, and the Maclaurin series for g is given by this. You can see it's alternating because it's got -1 to the n, and then x to the 2n plus 3 over 2n plus 5. So that's our formula for the nth term, starting at n equals 0. And then notice it's giving us the first three terms. And then plus ... that means it's going off to infinity. And as for the radius of convergence and the interval of convergence for g. So in this case, we would look right here, and you can see it's not geometric because we have n's that are not in the exponent. So usually the one you want to start with, if you don't see it's geometric, is the root ratio test. So let's use the ratio test on this. Okay, so remember the ratio test, you first find the limit as n approaches infinity. The absolute value, and then you replace all the n's with n plus 1. But remember, you don't really have to put this alternating part, -1, in there because of the absolute value signs. Those are always going to get rid of the negative anyway. So it has no effect on it. You can put it in there, but it won't matter at all. So you can just focus on the other parts here. So we'll have x, and we'll replace this n with n plus 1. And we have a plus 3 over, replace this n with n plus 1 as well. And then remember, you divide that by the original formula with just n in there. And dividing by this is the same as multiplying by the reciprocal. So it would be 2n plus 5 over x to the 2n plus 3. All right, so let's go ahead and simplify these so it's a little easier to see what to do as our next step here. So it'll be the limit as n approaches infinity. And if you distribute out the 2 to both of those, we'll get x, that'll be 2n plus 2, but then we can add that to the 3 that's up in the exponent to give you plus 5 over, if we distribute this 2, we get 2n plus 2 plus 5. So that'd be 2n. And then the 2 plus 5 would give you plus 7. And then this one's already simplified. 2n plus 5 over x to the 2n plus 3. But now let's see if there's anything we reduce before we plug in infinity. Notice 2n plus 7 and 2n plus 5, those are different factors there, so those don't cancel at all yet. But the ones that have the same base of x, when you're dividing, you can subtract the exponents. So notice when you get 2n plus 5 minus 2n plus 3, the 2n's cancel out, and you just end up with 5 minus 3 gives you 2. So this would be completely gone, and now we would just have x squared. And then, once you simplify that, you can realize, well, the infinities, the terms with the n's here, are never going to get affected by the absolute value sign, so you can plug in infinity to those outside the absolute value. And when you do that, the plus 5 is negligible, so we get 2 infinity over, same thing on the denominator, the plus 7 is negligible, 2 infinity. And then the only thing that could be affected by the absolute value signs is the x squared. And with the ratio test, in order to converge, remember that has to be less than 1. So then you can see the 2 and the infinities cancel out here. So all we're left with is the absolute value of x squared is less than 1. But this is a special case because it's not a linear one like they usually are. So just think, if you square something, that's never going to be negative. So in this case, the absolute value has no effect on this. So it's as if it isn't even there. And then right here, it might be tempting to take the square root of both sides. But with the trouble of that with an inequality as opposed to an equal sign, you'll get that plus or minus, and then the inequality sign wants to go both ways, which it can't do. So a better way to solve that accurately is to get one side equal to 0, and then factor it. Oops, that should be 0 there, sorry about that. Subtract the 1. And then test on the number line. See, the two things that make it 0 are negative 1 and 1. And then when you test, if you test negative 2, that's a negative. Negative 2 minus 1, negative. Negative times a negative is positive. If you test 0, that's 0 plus 1 is positive. 0 minus 1 is negative. Positive times a negative is negative. And then you can use the shortcut too. When you test 1, you can see 1 comes from a factor with an odd exponent, so it is going to change sign there. And in this case, since we're looking for where this is less than 0, we're looking for the negative interval, which is right here. So we can see it would be negative 1 is less than x, which is less than 1. But remember, the ratio test is inconclusive when it equals 1, so we don't know whether the equal to sign should go on either one of these. So we have to test the endpoints one at a time back in the original one. And that's when this alternating part could have an effect here. All right, so let's first plug in negative 1 for x. So let's let x equal negative 1. So we'll have the sum from n equals 0 to infinity, and then plug in negative 1 there. So we'll have negative 1 to the n, and then plug in negative 1 right there for x. So it'll be negative 1 to the 2n plus 3. Over 2n plus 5. And then notice these have the same base, so you would add the exponents. So you can simplify that to be negative 1 to the 3n plus 3. All right, and now let's see if this would make it alternate or not. Well, if you plug in 0, you're going to get 0 plus 3. That's odd. So it's going to be negative. If you plug in 1, you get 3 plus 3. That's even. If you plug in 2, that's 6 plus 3. That's odd. So it does alternate back and forth with this 3n plus 3 as the exponent. So you can use the alternating series test and then use this part as your a sub n, 1 over this. So we first would find the limit, so we're using the alternating series test here. The limit as n approaches infinity of what's left here is the 1 over 2n plus 5. And then when you plug in infinity in there, you get 1 over the plus 5 is negligible. Since you have infinities left on the number, that is 0. So that's the first check to make it converge. And then you just have to make sure the terms keep getting smaller. So if you find the first 3 terms, you can usually tell if they are going to get smaller or not. So if we plug in 0, we get, again, you ignore the alternating part, 1/5. If you plug in the next number to get the second term 1, you get 2 times 1 is 2 plus 5, that gives you 1/7. If you plug in 2, 2 times 2 is 4 plus 5, that will give you 1/9. So you can see the terms do keep getting smaller. So it does converge by the alternating series test. That means we would add the equal to sign there on the negative 1. And then let's check and see if it would converge or not at x equals positive 1. So at x equals positive 1, we get negative 1 to the n, and then we'll plug in positive 1 here. For x. But remember, 1 to any power, positive 1 to any power is just 1. So that goes away, and we're just left with n over 2n plus 5. And this negative 1 to the n, when you plug in 0, it's even, 1, it's odd, 2, it's even. So this is going to make it alternate too. And notice the thing that we have left here using the alternating series test is identical, 1 over 2n plus 5, to this one here. So there's no need to test it again, that we're going to get the exact same results. So this one's also going to converge, which means we put the equal to there. So you can see the center here would be 0. You can also tell because when you set this equal to 0, you get 0. And then the radius from here to here and here to here is 1. So your radius of convergence. Is 1. And then the interval of convergence. You can write interval notation, or you can just write it just like this. Negative 1 less than or equal to x, less than or equal to 1. Either way is correct. All right, now let's take a look at part B on this problem. For part B, now it asks for the first 3 non-zero terms, so the first 3 terms that aren't 0, and the general term of the Maclaurin series, because it is centered at 0, notice, for g prime of x. All right. So let's first write out what we know about g of x before we find g prime. And the nice thing is they already gave us the first 3 non-zero terms of g of x. So we could write that down first. If we give us x to the 5th over 5 minus x to the 3rd over 5. Minus x to the 5th over 7. Oops. Plus x to the 7th over 9. And then plus, and then where you can put the general term is right after this, after the plus dot dot dot. And the general term for this is right here. So that's the negative 1 to the n, x to the 2n plus 3, oops, over 2n plus 5. All right, and now, it might look a little weird, and it's plus dot 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 because it keeps on going to infinity. When you take the derivative, you just use your normal derivative rules. It's just the general term looks kind of weird, but the other terms are pretty normal here. So just using the power rule, since these are add subtract, you bring down the 3. So it'd be 3, and then you subtract 1 from the exponent, x squared, and the constant just stays there over 5. Minus, bring down the 5, subtract 1 from the exponent, x to the 4th over 7 just stays there. And then bring down the 7, subtract 1 from the exponent, x to the 6th over 9. And we really do the same thing on the general term, it just looks more complicated. Notice the only part that's a variable is the x. Remember, n's are just constants. So we're just going to use the power rule on this part. The other part stays the same. So negative 1 to the n stays the same. And the 2n plus 5 stays the same. And then we use the power rule on this one. Remember, just like these, you first bring the exponent out in front. So we'll have 2n plus 3. And then you subtract 1 from the exponent, just like we did here. So if you take 2n plus 3 minus 1, that's just going to be 2n plus 2. So that would be the derivative of the general term. So those are the first three non-zero terms and the general term for the derivative. All right, let's take a look at one more that's a little bit different. This time we have a function f given by this. So here's our formula for the general term here. And again, it gives us the first three terms. And notice it puts the general term in here as well. All right, so this one, again, we're asked for the radius of convergence and the interval of convergence for this Maclaurin series. So again, it's not geometric because we have this n that's not in the exponent. If it was just these two, it would be. So we would start with a ratio test again. So it'd be the limit n approaches infinity. Absolute value, plug in n plus 1 for all the n's. So we'll have -4. You plug in n plus 1 and there's a minus 1, the 1's cancel out. So it's just now -4 to the n. And I'll just put this on the numerator along with it. So x to the n plus 1 over n plus 1 for this n. And then remember, you divide by the original formula, which is like multiplying by the reciprocal. So this n would be on the numerator. And we'd have -4 to the n minus 1. And then x to the n. All right, and let's see what we can simplify now. So when you simplify, notice x to the n plus 1, x to the n, those have the same base. So you'd subtract the exponents. N plus 1 minus n would just give you 1. So just be x to the first now. And these have the same base, so you'd subtract the exponents. So if you go n minus n minus 1, notice the n's cancel out, and this becomes plus 1. So it just becomes -4 to the 1. But then what the absolute value does, it changes that negative to be a +4. So it'll be -4 to the 1, which becomes +4. And then when you plug in infinity to the n's here, those are not affected by the absolute value signs. So that would be infinity right there. And the plus 1 is negligible, so infinity right there. And then we have x is the only thing that could be affected by the absolute value. And again, with the ratio test, that has to be less than 1 to converge. So this time the infinities cancel out, and what we're left with is 4 on the outside. Absolute value of x is less than 1. So this time, to solve this, it's just linear, but we do have to get the absolute value by itself first, so you divide by 4. So you get the absolute value of x less than 1/4. So remember, to rewrite this, this is like saying the distance away from 0 is less than 1/4. So that means it'd have to be between -1/4 and +1/4. But again, with the ratio test, it's inconclusive when it equals 1, so we don't know whether right at -1/4 and 1/4 it converges or diverges. So just test them one at a time again. So let x equal -1/4. Back in the original one right here. So that would be the sum from n equals 1 to infinity. And we've got -4 to the n minus 1. Whoops. And then x to the n. And that's where we're going to plug in the -1/4. Over n. All right. So this one's a little bit trickier to simplify here because they don't seem to have the same base or the same exponent. So the trick is to realize, well, you can actually rewrite this We've got -4 to the n minus 1 here. And then the -1/4, you can really bring that up and make it negative on the outside. 4 to the -1 is the same as 1/4 to the n over n. And then you can multiply the exponents. So you have -4 to the n minus 1. And then when you multiply those, you have -4 to the negative n over n. And now they have the same base, so we can add the exponents. And as we do that, the n's cancel out, and we just get -4 to the -1 over n. And since that's a constant, -4 to the -1, you can pull it outside the series, and then all you'd be left with is 1 over n. And then that fits P series, where P equals 1, so that's less than or equal to 1. So that diverges. So you would not add the equal to there. And now let's try the other endpoint of positive 1/4. So with positive 1/4, still have -4 to the n minus 1, positive 1/4 to the n over n. And we can use a similar strategy here. Except this time, when we make this is going to be 4 to the -1. We want this base to be 4. So we can actually split this up into -1 to the n minus 1 and 4 to the n minus 1. And then when we write this as 4 to the -1 to the n, that will become 4. We multiply -1 times n to the -n over n. And again, you can add the exponents, so you get 4 to the -1. So we have -1 to the n minus 1. Whoops. And add the exponents there, so the n's cancel out again, so we get 4 to the -1 over n. And you can just bring that to the bottom, to the denominator. So it becomes 4n. And then notice if you plug in 1, you get 0. Plug in 2, you get 1. Plug in 3, you get 2. So you can see it's going to go back and forth between even and odd exponents. So this is going to be the alternating series test. So then you would just find the limit as n approaches infinity of this 1 over 4n is what's left. That's the part that doesn't make it alternate. And you can see that would give you 1 over 4 infinity, which would be 0. And then if you test the first 3 terms, if you plug in 1, your starting number, that would be 1 over 4. Plug in 2, 1 over 8. Plug in 3, 1 over 12. So they do keep getting smaller. So it converges. So that one will have an equal to. So on your number line, you can see it's going from -1/4 to 1/4. So the center again is 0. So this time you can see the radius of convergence would be 1/4. And then the interval of convergence we got right here. So it'd be negative 1/4 is less than x, which is less than or equal to positive 1/4. Or again, you could write interval notation. And then last part of this one, part B, this time it wants the first 4 non-zero terms of f prime, the derivative. And then it's got an extra thing that says express the derivative as a rational function. We'll see how to do that. All right, so let's write down f of x first, what it gives us. This time, notice the first 4 terms. So it gave us the first 3 of the original function. So let's write those down first. X minus 2x squared plus 16/3 x cubed. But we need to figure out one more in order to have 4 terms on our derivative instead of just 3. So let's go ahead and plug in. So the starting number is 1, so that's 1, 2, 3. So now we'd have to plug in 4. So if we plug in 4, we'll get negative 4 to the 4 minus 1, that's just 3. So negative 4 to the third, negative 4 cubed is negative 64. It should be negative 64. Over, plug in 4 for that in. Now it does reduce, but I'm not going to do that because it'll be simpler if we don't. We'll see. And then this would be x to the 4th. Plug in 4 for it. And then notice it doesn't ask for the general term here. So I'm just going to put plus dot, dot, dot. All right, so now let's find our derivative. The derivative of x would be 1 minus 4x plus 16x squared. This is why I left it like this, because when you bring down the 4's cancel out. Minus 64x cubed. Okay, so that's the first thing it asks for. And then notice it asks as a rational function. Well, that's rational, just another word for a fractional function. So it's a little tricky on how you're going to do that until you notice the pattern. Notice from 1 to negative 4x to 16x squared, negative 64x cubed. You just have to notice this is a geometric pattern. The original one was not geometric, but the derivative is. And notice the common ratio, multiplied by negative 4x each time. So if we wanted to see where it converges, we would put that between negative 1 and 1. But as a rational function, we want to express this. So remember what this is going to equal is using our sum formula. For a geometric series, remember the sum would be the first term, a sub 1, over 1 minus r. So in this case, what this is going to equal, f prime of x would equal, the first term is x. Sorry, not x. It's looking at the wrong one. First term of the derivative is 1, because this one's not geometric. This one is 1 over 1 minus, we just figured out r is negative 4x. So the way we can express the derivative as a rational function is 1 over, the negatives cancel out, 1 plus 4x. So that now we have it as a rational function as opposed to a polynomial. And that includes the notes for AP Calculus on the topic of common Maclaurin series with derivatives.